So welcome everyone for this talk in the CS Colloquium series at the Hebrew University. We're very happy to have Vincent Cohen Addad, who is coming to us or talking to us from Google Zurich. He's a research scientist there and he's on leave from the Sorbonne University. Vincent has done some really amazing and breakthrough work in the past few years in the design of algorithms and clustering and network design problems. He won a lot of very prestigious awards. He won the Marie Curie Fellowship in Copenhagen, and his PhD thesis was awarded the EATCS Distinguished Dissertation Award. We're very happy and excited to have him to tell us about some recent progress on the inapproximability of high-dimensional clustering, and the stage is yours.
Okay, thanks a lot, Ilan, and thanks a lot for the invitation. I'm very happy to be presenting today. Too bad I can't come. I would love to visit, but yeah, that for better time. Okay, so this is a joint work with Kartik that some of you may know because he spent a lot of time in Israel, and with Weong Lee from now at University of Michigan. Kartik is now at NYU. Okay, so this talk is about clustering, and it's going to be mainly about clustering in high-dimensional Euclidean space. And so here we want to look at clustering for the following reasons. We want to have, basically we have as input a set of points in a metric space. So we have distances between points that satisfies triangle inequality. Maybe some more constraints, but at least triangle inequality. And the goal is to find a partition of the points such that points that are close to each other end up in the same part of the partition. Okay, and this is like very fundamental application. One of them that we have been playing with a little bit is for redistricting facility location. So where your distances represent how close points are, in real life. For example, how close you are to your neighbors, some city centers, and so on. And these are motivation in redistricting and facility location. And then, of course, there is the more more sexy these days application, which is coming from machine learning and AI, which just say that you have distances between elements, between data elements that represent how similar data element are. So if two data elements are very close under my distance metric, they are very similar, and otherwise they're very far. And then the clustering helps you find hidden patterns in the input data by finding points that are close to each other, that are similar to each other, from points that are far away from each other, that are meaning different things. Like here you would put the duck together or long ears animals together. Okay. So this is for the very high level motivation, but then as a computer scientist, maybe what we want to do is also have a more formal variant formulation of the problem. And here we'll define it by the key clustering, which is just the slightly more general view than classic things, which is as follows. So you, as input, you get a set of what we call clients, so a set of points that by historical reason is called clients, and the parameter k, and your goal is to find the k representatives that we often call centers, such that you minimize the following quantity, which is that you take the sum of all clients to the closest representative, closest center, and the cost you're going to pay is depending on the distance. And so if you are looking at the key median objective, the cost is just going to be distance. If you are looking at the key means objective, we'll look at the distance squared. And these two objectives have a lot of history. They have both pros and cons in practice. It's just for historical reason there are two of them, and we're going to see the differences between them. Okay. So So in fact, this problem of, I give you a set of points and then I want to find the point that is that minimizes the sum of distances to the input point, finding the one representative that minimizes, let's say, the sum of distances is a very old problem. It dates back to the 17th century. And in fact, Fermat asked about it in the letter. It just has the following, easier question, which is I give you 3 points A, B, C in R2, and I want you to find D that minimize the sum of the distances to D, of A, B, C to D. Okay, And okay, and then there is Torricelli who replied, gave some nice construction, but then turns out that if you have more than 3 points, even in R2, it starts to be hard to compute exactly. And in fact, you end up being like fighting with over numbers that are not rational, and you have to define the model properly. But you can approximate it up to 1 plus epsilon factor in like some few gradient descent steps. So
What does it mean hard to compute? Is NP complete or just we
so
don't know how to compute it?
Okay, so we don't know how to compute it, and it's likely not to be in NP because you can't express it as rational and stuff like that. So you're really like beyond like you are complexity classes that are like for points that have like that are not that have no nice representation.
Mhm.
So it's not that easy to yeah, I don't. So okay, the point is that I'm not very clear because it's not very clear what's the complexity class of this problem. So it's beyond NP, but nobody knows what's the right complexity class. So I think this is maybe the first open problem of this talk, is like can you characterize what's the complexity class of the problem of the 1 median problem? I give you n points and even in d dimension, and can you show that it's like so the problem is strongly convex. But if you run, you will need to run for too long if you want to compute to reach the optimum. So okay, so that's the first problem. So in order to avoid just this, so this is for exact exact results. So sometimes we just want to avoid this issue with this 1 median. If you are looking at the 1 means, like this is also really coming from the fact that I'm looking at the L2 distance, the Euclidean distance in the plane. And that I'm paying the sum of distances. If you move to the sum of square distances, then it's the means, and the minimizer is the mean. So I can just like compute the average of the coordinate of all the points, and then that gives me my minimizer. So it's really coming from this weird structure that it's like the sum of distances under the L2 norm. So to avoid this type of issues, what we're going to look at is like this discrete variant, where it's the same problem as before, except that in addition to the client set and the parameter k, I'm going to give you a set of centers, of candidate centers, some point of the metric, and now you have to pick k of them, but k centers among this set of candidates that I'm giving you, and then then now the one center, one median is easy, right? Because I can just enumerate over all of them, compute the cost for all of them, and at the end of the day I would put like the minimizer. So I avoid this caveat of like having to look at having to deal with this like infinitely many candidate centers. Okay, so this is just like a technical thing, but it's to make things clear. Okay. So what do we know about this problem? That as you can see, like for the 1 million, it dates back from the 17th century. From the 2 million now, okay, so we have to like fast forward to 21st century. So we know that it's NP hard when k equals 2. So that's interesting. It's NP hard in R2. So now so k equals 2, but many dimension. And also, it's in low dimension, it's also NP hard, but then this requires that you have many like k is large, k is like almost n, almost the number of points. So there is kind of like two orthogonal direction. Either you have like many dimension, and then that's hard even for 2 centers, or it's a few dimension, but then if you have many centers, then it's hard. And in fact, it's W2 hard in general metric. So you can't like, okay, and if you believe in ETH, for example, we won't be able to, in the exponential time hypothesis, we won't be able to get an exact solution in better than n to the k. So basically, the enumeration of all possible k tuples among your candidate centers is the best algorithm you can think of, assuming ETH. Okay, and now for Euclidean, so that was mainly for like exact computation. So we know that it's NP hard. Okay, so what can we do? So we may want to turn to upper bound, to approximation algorithm, and that's where it starts to be interesting. I think so when the dimension is arbitrary, one can get for k-min, so distance squared, one can get a 6.357 approximation using a pretty recent result. And as far as I know, it's the only result that gets you an approximation that is good, that can use the Euclidean structure to get you a good approximation, a better approximation than what's known in the general case. Okay, when the dimension is constant, then one can get a near linear time. We showed that last year at Fox. We can get a near linear time 1 plus epsilon approximation, but the running time now is doubly exponential in dimension. In fact, it's like 2 to the 2 to the 2 to the d. So it's like but then n log n. But of course, that's like so. So if your dimension is fixed, then you can get a p-test basically. But otherwise. And also the other thing, right? If the dimension is really large, but k is fixed in Euclidean space, then I can get a constant p-test as well. So if the dimension is fixed or k is fixed, then I get a p-test. But if k and the dimension can be polylog n, then I must use this 6.357 approximation. That's what we know. Okay, and for general metric, we get a 9 approximation by the same paper, okay, or a 2.67 for k-median. And here, what I find interesting is that this paper here really manages to extract more structure from Euclidean metrics than what they can do in general metrics. So in general metrics, you only have triangle inequality. Now in Euclidean space, you can't if the triangle inequality is tight, it means that you have really points that are almost aligned, right? And then you can maybe use this information to design a better algorithm. Like if that's the worst case, maybe you can handle it in a different way algorithmically. We'll see that you see more about that in the meanwhile. Okay, and maybe the last thing is that for fixed k again in general metric, we showed also at ICAP last year that one can get 1 plus 2 over E approximation, which under ATH is tight. So if you want an FPT algorithm, fixed parameter in k, so basically 2 to the k poly n algorithm, then you can get a 1 plus 2 over E, and that's probably the best you can do, unless you can do refute ATH. Okay, so now let's move to hardness of approximation, which is like the topic of this talk. So for general metric, there is this work from the late 90s, which shows that for k-means you get this 3.94, or for k-median you get 1.74. And this is actually this 1 plus 2 over E. It's the same value. I should have made it clear, but this is like 1 plus 2 over E. Here is actually the same value that is appearing here. Is like the general lower bound for k-median in general metric. In general metric, meaning like triangle inequality is the only thing that helps, like that the only constant you have on the metric space. Okay, and for L2 and L1, there was a major gap here, because as we have seen, it's not that the approximation algorithms are much better. It's not that we know how to use the Euclidean structure to get much better result. As I said, I'm really excited that one can get better than improve using the Euclidean structure, but the bound is still 6.357, so it's pretty high. But then what was known from the 2000 was that for L2 and L1 metric, for k-means and k-median, there was known that you can't have much, maybe there was a 1.0001 lower bound. So there was a pretty huge gap between k-means with 0.10001 and 3.94. There's a huge gap between Euclidean and general metric in terms of hardness. For an infinite metric as well, same thing, pretty small hardness. And for the continuous version, where you can pick your center for k-means arbitrarily in the Euclidean space, there was a recent lower bound in 2017, which was showing 1.0013, which was the hardness. And still, the best upper bound was still like 6.357 or something.
Vincent,
yeah.
Sorry to interrupt. There is a question in the chat which I think might be relevant for many people.
Sorry.
Can you briefly tell us what, when you mean k-means equals to some number, what do you mean by that number? What does it mean? What does it mean, the approximation ratio? If you could explain what it means. That
sure. So sure. Yeah, so it means that there is an optimum solution, which is like the solution that places the solution with k centers that minimizes the k-means objective, which minimizes the sum of the distance squared from each point to the closest center, and that's the optimum solution. That's the optimum value. Now, when we say that it's a C approximation to this, it means that the algorithm will output a solution whose objective value is at most C times this optimum solution that I just described. Okay, so you have the optimum that achieves some number x, and if we have an algorithm that is a C approximation, we are granted that the value of this solution is at most C times x. Did that make sense? Did that clarify?
Yeah, to me it did. I hope that it's also okay for everybody else.
Yeah.
If not, please ask questions.
Yeah, please interrupt. Yeah.
I don't ask this algorithm that gets a C solution. Are there any limitation on the algorithm? Does it have to be polynomial, for example?
Yeah, exactly. It has to be polynomial. Yeah, it has to be a polynomial term algorithm. So that's what. Yeah, we are looking after a polynomial term algorithm, but sometimes we in my previous slide, for example, here we might in this slide here we might say that okay, polynomial, but okay, if we think of dimension being constant, if we have an algorithm that is like n to the d, then where d is the dimension, that's polynomial if we think of the dimension being constant. So that's why maybe we get better bounds if the dimension is constant. We can have an n to the d algorithm that will give you like maybe a 1 plus epsilon. In fact, here it's like 2 to the d n log n algorithm. And the same here, if the number of clusters you are looking for is k is a constant, you think of it as a constant, then 2 to the k is now poly n. That's polynomial time as well, because 2 to the k, if it's 2 to the constant, so that then you're happy. So indeed, for these special cases, we can get better results than for the general case. But yeah. And what we are saying here, also here, maybe something that I didn't say is that even if I give you, if you want to go faster than n to the k, then which is like in the general case, if you want to go faster than n to the k, then you can't get better than. Sorry, if you want to have a good approximate, what did I say? Yeah, if you want to get faster than n to the k, then you must have a 1 plus 2 over e approximation. So you can't get an exact algorithm with n to the k, but you want to, but you can still get, some approximation. Okay, so I'm going back to this. Okay, and what we showed is that it's hard. We improved the hardness. We improved that for all these metrics, for all these different metric L2, L1, and this problem k-median, k-means, there is no. If you believe in like p different from np or the Euclidean conjecture, I'm going to get to that later on. But basically, if you believe some like on some strong hardness condition, so strong conjecture, like conjecture that people in complexity may believe, then you can't have an algorithm, a polytime algorithm that gives you better than 1.15 approximation for the k-means problem. That cannot approximate the optimum solution with a better than 1.15 approximation in polynomial time. You can't have such an algorithm if you believe this conjecture. It will refute, like, it means that you have a bright idea and you will refute some of the important conjecture in the approximation algorithm. So we improve. So basically here we improve all the known results. And I'll try to give you. I think the proof for showing this hardness result is going to be pretty straightforward and easy. And it probably, it's interesting in the sense that it shows how fundamental, how basic this clustering problem are if you are interested in complexity or algorithm or like what you can compute efficiently in general.
So this lower bound is for arbitrary k, right?
Arbitrary k, yeah. Arbitrary k, arbitrary dimension. Yeah,
while
exactly.
Well, the upper bound from the previous slide was for constant k or fixed k.
So yeah, except this one that works for any k and any, except the top one, that works for any k and any dimension.
Thank you.
Okay. So we also improve for the discrete and the continuous. And let me now try to give you a little bit of insight on what is going on here. Okay, so when you want to prove lower bounds, you may want to, there are some basic problems that we know. It's like that are very fundamental, that are used to prove lower bounds and hardness and characterize what one can compute efficiently or not. And probably everyone has heard about SAT or this constraint satisfaction problem. There is label cover, which is one specific instance of this family, which is also used for computing hardness of approximation or like different problems. And then there are problems that are much more that you are maybe a bit less. They're a bit more specialized, but maybe still you've heard of them. Like there's the set cover, where I give you a universe, a set of elements, and some sets that contain some of the elements, and you want to pick as few sets as possible so as to cover the whole universe. And so these are like very fundamental problems as well, because they appear in many applications. Very fundamental in the sense that they have led to many development in approximation algorithm and hardness results. So very basic problems. And then along this line, there are more and more specialized problems, like max cut, independent set, very fundamental as well, very well studied, but maybe a bit more specialized. And then at the end of this line, there are some problems that are very, very important in practice, like clustering, like network design problems. They're very, very specialized. They're really close to our everyday life in the sense that they like the metric, this metric constraint that we have are really useful in practice, right? We often do deal with metrics in real life, right? When you build a network, your network, the length of your paths or roads, and they're going to satisfy triangle inequality. There are maybe more constrained even on that. For clustering, we have these distance measures. So they are all very important fundamental problems that have metric structure. And so they are very specialized and not very, as fundamental, for example, as set cover or like, CSPs. And the unique game, conjecture is around here. It's stating some condition on some label cover instance that, you can't solve them with so much accuracy. I'm not going to go too much into that because it's not going to be a course on hardness of approximation. I just want to give some insight on we're going to just assume some result on that and see how we can use them to go to clustering here. And we are going to go from Euclidean games to Vertex Cover, actually a variant of Vertex Cover, and then end up in clustering to show some new hardness result, as I stated. So the hardness result were improving over the low bound from the early 2000s. So it's like a pretty big important improvement over what was known. Okay, so how do we prove hardness for points in Euclidean space? So a natural path for proving hardness in Euclidean space would be that you start in a general metric, okay, because the constraints there are are much easier, right? So I can try to find the low bound. I can find a hard instance in the general metric, okay, and there, if I want to build a hard instance, the only constraint I have to place on my distances are triangle inequality. That's the only thing I have to satisfy for it to be a valid input to clustering. It just has to satisfy triangle inequality. So I can try to build a gadget that just satisfies triangle inequality, and that will give me some hardness result for the general metric case. Once I have this general metric case where points satisfy triangle inequality, then I can try to take this gadget and embed it into a Euclidean space of even large dimension, like n dimension even. Okay, I can try to take my gadget, my triangle inequality gadget, and then embed this clustering instance into Euclidean space of n dimensions. Okay, and then we're happy, we're done. Okay, because if you can solve it, in the Euclidean space, then maybe you could solve it in the geometric case. But in fact, if you could solve it in the geometric case, maybe you will solve P equals in P. So that would be the proof path. Okay, of course, it's research. It doesn't work the way you want it to work. You realize that in fact you can't embed such a gadget without messing up the distances, because when you go from general metric case to Euclidean space, you have to change some of the distances, because it's not that every general metric space can be embedded into a Euclidean space of high dimension. In fact, because now you have to when I'm working in a general metric space, I'm just setting up distances between points, and if they satisfy triangle inequality, I'm done. Now, if I go to Euclidean space, I need to find the actual location, the actual coordinate of the points, and this coordinate of the points. Then, if I take the L2 distance, they should satisfy. They should be nice, so that the gadget is preserved. And so sometimes you can't find the coordinates so that they satisfy what you want. And we'll see an example very soon. Okay. So let me show you the proof for the general metric case, which is not our proof. It dates back from the 90s, but it's actually very enlightening if we want to understand the rest. So we'll start with the max coverage problem, which is just like set coverage, just a different perspective on set cover. but it's a very fundamental problem as well. I give you a universe, so just a collection of elements from 1 to n, let's say, and a collection of subsets of these elements, okay, plus a parameter k. Okay, this parameter k is going to be more or less the number of clusters we want for clustering, but let's not worry about that now. And the objective is to cover a maximum fraction of the universe while picking at most k subsets. So you can pick k subsets among your sets, but I want you to cover as many elements of the universe. So of course, some sets may overlap. So if you pick the 2 of them, you only cover, you lose. You don't cover the whole thing. So you need to pick sets so that you cover as many elements as possible. The set does not disjunct. Okay, and there is this theorem by Feige. Is there a question?
Yes, someone wants to know if you can please explain what's a gadget.
Oh, a gadget? Yeah, a gadget is just like some construction that we'll make to transform a hard instance for a specific problem. For example, set cover. We'll try to transform this hard instance into a hard instance for clustering. And now, if you can solve the hard instance for clustering, the gadget will tell you how to solve a hard instance for set cover. So this gadget is used to establish connection between problems, in the complexity sense, in the sense that if you can solve one problem fast, then you can solve the other problem fast. So that means that if we believe that this problem is hard, this problem is hard also. So that's how you connect problems. You make what we call gadget, which is in fact how you encode one problem into another one. And we will see an example. I'm going to go and describe an example right now of a gadget.
Okay, there's another question. Does this lower bound also hold for any arbitrary distance function like squared Euclidean? The lower bound distance?
Which lower bound actually is that?
I think it related to the previous slide that you showed. Sorry, that go forward.
Forward or back?
I think so. Maybe the speaker wants to jump in or the person who asked the question.
Yeah, feel free to interrupt if you.
Hi. So So this slide. So yeah.
Yeah.
So does this hold for the squared Euclidean also?
For the what? Sorry.
For any arbitrary distance function,
No, like this holds for L1 distance, which is like the L1 norm between the vectors, L2 norms, and L infinity, and the objectives are k-means, k-median.
Okay.
And for arbitrary distances, we can get higher lower bound because we can make more difficult instances.
Okay.
So for arbitrary distances, if you just allow me triangle inequality, I can construct a harder example, and that's what I'm going to do in here.
Okay, thank you.
Sure. So here is an example. Okay, we'll see an example of a gadget very soon. So there's this theorem. So okay, what does the theorem say? So the problem is clear. I'm just going to repeat very quickly. Set of universe elements 1 to n, and a set of subsets of these elements. You want to pick k subsets so as to cover as many elements, so that your set contains the union of your set contains as many elements as possible. Okay, and this problem is hard in the sense that you can't distinguish between two instances that have the following properties. I give you an instance where there are k subsets that can cover the whole universe. Okay, so max coverage is 1. You cover everything. The fraction you cover is 1. That's one instance. And I give you a second instance where, in fact, the best k subsets can cover at most 1 minus 1 over e plus epsilon fraction. So it means that, and these are two different instances. I can give you a family of these instances, but there is no algorithm that can really distinguish between the two. Okay, it's computationally hard to have an algorithm that will, for all of these instances I give you, will be able to classify them correctly. Yes and no. Okay, but the decision whether it's an instance where you can cover everything versus you can't cover at most, you can't cover more than 1 minus 1 over e fraction. This decision problem, yes or no, it's hard to solve. It's like NP hard to solve this decision problem. Okay, so now I know that this problem is hard. Okay, and I want to show that my k-median objective is hard as well. How will I do that? Well, this is where I use a gadget. I'm going to take my instance from set cover, this hard instance that I want to decide whether it's yes or no. And I'm going to turn it into an instance for clustering. And, then I'm going to say, oh, if you can solve this instance for clustering, if you can get a good approximation for this instance of clustering, then you can solve the set cover instance very efficiently. Okay, so that would be a contradiction, right? Because we believe that the set cover is hard, as we showed that actually it's NP hard. So if you believe in P different from NP, then you can't do it. And if you can't do it, then you won't be able to solve my clustering instance. So how do we create this clustering instance? So we'll make a client, a point that you want to cluster for each element of the universe. Okay, so you have element of the universe, U1, we create a point. For element universe U2, we create another point. For client universe U3, we create another point, and so on. So we have endpoints that are my universe elements. These are my client. Okay, so I take my set cover instance and creating a clustering instance. And then I will create the candidate centers. And the candidate centers, I'm going to create them very easily. I'm going to create a candidate center for each of the set. Okay, so maybe this candidate center here it corresponds to set 1. This candidate center is set 2, set 3, set 4, set 1. Okay, so these are my points. I have created the candidate centers. I have created the clients. These are the points. Now, to finish the constructing the clustering instance, I need to set the distances. Okay, and these distances, they need to satisfy triangle inequality. So what I'm going to do is I'm going to say, okay, U1, my universe element 1, if it belongs to set S, then I'm going to put a distance 1 between U1 and the set S. And U2, if it doesn't belong to S, then I'm going to put distance 3. Okay, so now it's either 1 or 3. Distances are like this. Okay, and this, this gives me, this sets the distances for the whole instance. If 2 points belong to the same set, they are both at distance 1 from the set, so they are at distance 2 from each other. And if U1 and U2 belong to the same set here, maybe they are both at distance 1 here, so U2 must be at distance at most 3, and I'm going to set exactly 3 from this S. Okay, so that's okay. So I have taken my hard set cover instance, and I'm going to I'm translating into a clustering instance. And what I'm doing here is that what do I get? What do I get? So if the set cover instance was a yes instance where everything was 1, then it means that there exist k sets, so k candidate centers, such that each client is at distance 1. Each client is covered by the set, right? Because I cover everyone here. So I know that if I can cover everyone, then I can pick k sets such that everyone is at distance 1 from the corresponding candidate centers. Okay. So my cost, the k-median cost of this instance is going to be U, which is the number of elements in the universe. Everyone is at distance 1 from the candidate center because everyone is covered. So maybe sometimes, some points may be covered by multiple sets, but in the worst case, they pick 1. And there is no point that is not covered. Every point is covered by at least someone because everyone is here. So everyone is at distance at most 1. Okay. So if the max coverage instance I translated using this gadget was a yes instance, then the cost is U. Now, if it's a no instance, okay, if you gave me a no instance, I don't know which one, but I still apply the same gadget construction. I construct the sets, and now if it's if it's no, then it means that no matter which set of k sets, no matter which k tuple of the sets I'm going to pick of the candidate center, no matter which k candidate center I pick, I'm going to cover at most a 1 minus 1 over e fraction of the element. So it means that at most a 1 minus 1 over e fraction of the elements are at distance 1. Okay, so 1 minus 1 over e fraction of the elements are paying 1, and the rest they are at distance 3. Okay, because they are not covered. There is no one nearby them. No matter which set of k tuple I pick, fix 1, then there are at least a 1 over e fraction that is at distance 3. So what's the cost? Well, for a 1 minus 1 over e fraction of U, I'm paying 1, so I'm paying this. And for a 1 over e fraction of points, I'm paying 3. So the total is that I'm paying 1 plus 2 over E of U. That's the cost for the k-median on that no instance. So, so what do I get? I get that if it's hard to distinguish between yes and no instance for the set cover, then it's going to be hard to distinguish between 1 and 1 plus 2 over E approximation. Okay, so I can't get better than 1 plus 2 over E approximation for this problem. It's hard to distinguish between these two types of instances using my gadget. Okay.
So isn't it probably a little bit better because of the epsilon? So you
yeah. There is this epsilon, but let's I'm not talking about this epsilon. This epsilon is like arbitrarily small.
Yeah. Exactly.
So okay. So from this theorem we get, and that's a gadget. That's what I call a gadget. We get this it's a metric translation of the set cover. It's like you can see the clustering as a metric set cover using this gadget. And now what Guha and Khuller showed in the late 90s is that it's hard to distinguish between these two things. So it's hard to distinguish between yes instance where the cost is 1, like U, sorry, it's like X, the total number of elements, or where it's a no instance where like the cost is at least 1 plus 2 over E minus epsilon. So that's what we get out of this mess. Okay. And it seems to be the right answer. This 1 plus 2 over E approximation seems to be the right bound, in the sense that in some work last year at ICAP, we showed that in fact you can reach that approximation in time f of k poly n. And this is also tied for the same reduction, like the same hardness show if you believe in the exponential time hypothesis, which is another hypothesis, hardness hypothesis. Okay. And it's still open to get a 1 plus 2 over E approximation in poly time. The current bound is higher than that, so getting this thing would be great. Okay, so now let's move to Euclidean space. I showed you how to get this 1 plus 2 over E for the general metrics, and now what I would like to do is go and show that it's also hard in Euclidean space. So if you take the instance that I described and you try to embed it into Euclidean space, you won't be able to do it very efficiently. So the distances that I had before was 3, right? Distances that were 3. If I embed it using the result of Trevisan, they will become 2. Okay, so we lose already a bit in the approximation hardness, right? We it's less clear between the yes and no. Before, you had some point that were paying 3. Now they are paying 2. So the gap between the yes and no instances is already becoming smaller. But the worst thing is that some distances that were 1 before, now they are 2 minus epsilon for some constant epsilon that is tiny as well. So now the gap is so some in the yes case you will be paying 2 minus epsilon for everyone, and in the no case you will be paying 2 minus epsilon for 1 minus 1 over a fraction and 2 for 1 over a fraction. So and the difference is going to be very, very tiny. So it's like the constant epsilon here is it's going to be very tiny. It's like 1 over a times the constant. So it's really bad. So this because these two things have closed like this, the gap now becomes 1.001. So you can still show that you can't have a polynomial time approximation scheme that allows you to get a 1 plus epsilon approximation for any epsilon, but the gap is still pretty small, and so we are not very happy. And the issue we are facing here is that there is very little structure on the metric we are defining. Right? When I'm designing this gadget for the set cover, I have the clients. I have the sets, and each client can be in arbitrarily many sets. And also each set can contain arbitrarily many clients. So in the sense that, for clients, many of them are some client is at distance 1 for many sets and potentially, and at distance 3 from some other. And some set is at distance 1 for many clients and at distance 3 for some others. And there is no structure at all, right? It's like a complete mess. I mean, I didn't analyze how many clients on that side, and so on. And if it's completely arbitrary like this, if it looks like a click like this, a bi-click, where you have distance 1 and some of them distance 2 and so on, and you want still to preserve some of them distance 2, then you will have, you can't embed that into a Euclidean space. There is no way you can find coordinates. So embedding here means that I need to find coordinates for each of these points and each of these ones, so that now if I take the L2 distance between the vectors, I get the right distance. And you can't find that. You can't find that. It's impossible. Mathematically, you won't be able to find it for arbitrary distance. So what we can try to do is find a problem that is maybe a bit easier, but for which one can still get some hardness, and that will be more amenable for embedding. Okay. So let's look at the vertex coverage problem, which is a variant of the set cover, but somewhat easier. So the input is a graph where you have a graph G with vertices, edges, and a parameter k again. And your objective is to pick k vertices such that you cover as many edges as possible. Okay, so an edge is covered if it's adjacent to one of the vertex you have picked. Okay, so what happens is that now we have this more recent result from 2019, 2011, where it's unique game hard. So now it's not, it's a different assumption, but let's go with it. So it's hard. Let's just say it's hard to distinguish between an instance where you can indeed pick k vertices and make sure that you touch all the edges, or a no instance where no matter which set of k vertices you pick, you will only cover a 0.9292 minus epsilon fraction of the edges. Okay, so no matter which set of k vertices, there are still some edges that are not touched. And again, you want to decide, I give you an instance and I ask you to decide whether it's a yes or a no instance. And this is hard. This is computationally hard. You can't do it efficiently if we believe this conjecture. Okay. And this is almost like a set cover. It could be a set cover if we think of the edges as client, because this is your universe. These are the points you wanted to cover. And the sets that you are picking are the vertices. Each vertex covers some edges, and that's the set of elements it covers. But now this is much nicer because each client is an edge. The edges are the client. So each client is an edge, and so it's contained in at most two sets. So now the number of points that an edge, a client will be at distance 1, 2, is only 2. There are only 2 points, and the rest is distance 3. And we'll see that it's very, very nice to embed. Okay, so what we show is that this theorem implies that if you are in high dimension, let's say at least log n, then it's going to be hard to distinguish between an instance where you pay n prime, or where you pay 1.15 n prime for the k-means problem. Okay, and for the k-means in continuous, we get a slightly worse bound. But I'm not going to go too much into this. I just want to go into the key idea and maybe that's the. Okay, so remember that's the gadget we had. If I gave you a set cover instance, I was creating some clients for the universe. I was creating some candidate center for the sets. So now for this vertex coverage problem, I'm going to do the same thing. I'm going to say, okay, edges are here, are going to be clients. I'm going to put an edge for each client. Sorry, a client for each edge. And I'm going to put a candidate center for each vertex of my input graph. That's how I translate the input graph to the input graph of the vertex conventions to a clustering. Okay, but now there is a very natural embedding. So let's say you have n vertices. So let's say vertex vi is going to have 0 everywhere except at the I coordinate where it's 1. Okay, so you just number your vertices from 1 to n, and the ith vertex you put coordinate you put 1 at the ith coordinate. Okay. Now for each edge vi, so that's the point. That's going to be the point, the candidate centers that correspond to the vertex vi. Now for the edge vi vj, I'm going to create a client. And what's the coordinate? What are the coordinates of this client? I'm going to say, okay, if it's between an vi and vj, I'm going to put 1 at ith coordinate and 1 at j coordinate. Okay, very simple. It's an edge. It has 2 neighbors, vi, vj, 1 and 1. Okay. Okay, so that's the embedding. Okay, what do we get? Okay, let's look at an edge vi, vj. What is the distance from the points that correspond to the edge vi, vj to vi? Well, you remember vi, vj, and vi here on the bottom. they agree on all the coordinate. Even the i's coordinate is the same because it's vi and vivj, except the j's coordinate, because the j's coordinate is 1 here, but it's 0 there. So, the distance between the point corresponding to vivj and the point corresponding to vi is the same as the distance between vivj and vj is 1. I take the square distance because it's a k-means objective. So, the L2 squared is like this, 1. If I take a center VL, then what's the distance? Well, VL, if you replace here with VL, then it's 0 everywhere except on the L coordinate. And here it's like 1 only on I and J. So now they differ on 3 coordinates. So before they were differing on 1, now they differ on 3. So the distance from vivj to VL square is 3. Okay, but now we are very happy, right? Because this is exactly what we had before in the general metric case. If you were covered by a candidate center, like by the set corresponding to candidate centers, the distance was 1. Now now it's the same. If you are adjacent to one vertex, the distance is 1. And if you are not, if it's a different set or different vertex, then it's 3. So, it looks very similar. It's the same pattern. So directly you get out of this is that if you get a vertex coverage is 1, if it's a yes instance, you apply this embedding, you get the embedding. Now you look at the k-means objective on this embedding with these candidate centers, and you get that, if it's a vertex coverage where you can cover everyone, it means that I can pick k candidate centers and make sure that everyone is covered, meaning that every edge is a distance 1 from the corresponding candidate centers. So what I'm paying here is the number of edges, which is the number of clients. I'm paying this. And if it's a no instance, which is that the vertex coverage is at most 0.9292 minus epsilon, then it means that no matter which k-tuple of center I pick, it can cover at most a 0.9292 fraction of the edges, for which I'm going to be paying 1. And for the other, I'm going to be paying 3. So for the 1 minus 0.9292 fraction, I'm going to be paying 3. And so in total, I'm going to be paying 1.15 E versus E. Now, if you had an algorithm that can distinguish between these two solutions, between this clustering algorithm that can give you a good k-means, so that you very good approximation algorithm for k-means that can distinguish between these two instances, you will be able to solve this vertex coverage problem. Okay.
Do we believe that this 9292 number is tight?
Yeah, that's unfortunate. That's both unfortunate and surprising. There is indeed an algorithm that can give you this 0.9292 approximation for vertex coverage.
Wow.
Yeah.
Okay.
Yeah, that's what I feel sad. Okay. So what happened here? The pattern I was trying to follow was that, for the first step, you put hardness in the general metric case, and then you embed. And that was very nice. The embedding was pretty clean, very nice, 0.1, the way you embed things was really beautiful, very simple. The issue is that now the first step is kind of messed up, because before I was it was hard to distinguish between 1 and 1 minus 1 over E, which was 0.7 or something. And now I went from 1 to 0.9292, which is the gap is now 0.072. So the gap for the general case is really hard. It's really small, it's really tiny. So it's not a very big gap. And so, there is kind of a mismatch that we are trying to face here, which is that the step 1, you want a hard problem. So not vertex coverage. Vertex coverage is not so hard. You have a 0.9292 approximation. So it's not a very hard problem. It's giving you some little gap. So for the first step, you want something that is very hard. And for the second step, which is the embedding, you want to be able to embed it as nicely as I did in the previous slides, which is almost read the embedding from the problem. So we really want to make these two things connect. We really want to make them touch. And so in some new work, we have been working on a new problem, which is maybe a bit counterintuitive to look at first, but which we believe is the right problem to look at. And this problem is the following. So I give you a parameter t, which is think of t as a constant, maybe 15, something like this, large constant, somewhat large constant. And then what we say is that, I give you some edges, again, just following the previous notation, some edges. So these are just subset of size t from an n value. I give you, the n is like the universe size, and I give you subset of size t from n and a parameter k. And again, you have two cases that you would like to distinguish. So your goal is to find subsets of size t minus 1. Okay, so edges of size t, but I want you to find subset of size t minus 1, such that for each edge, okay, for each t in the edges set, there exists one of your t minus 1 subset that is fully contained in t. Okay. And for the soundness, so that's the hard part. And for the soundness, so that's if you can cover all the edges, basically. That's one type of instances. And for the other type of instances you get is no matter which subset of size k of t minus 1 tuple of n, the number of edges that contains at least one of them is only an alpha fraction. And we made this Johnson coverage hypothesis, which says that you have a 1 minus 1 over e plus epsilon. This alpha here, you can't cover a better than 1 minus 1 over e fraction. Like there exists, like for any epsilon, there exists a t epsilon, like let's say 1 over epsilon, such that if you look at 1 over epsilon tuples, then you can't distinguish between 1 and 1 minus 1 over e plus epsilon. And we believe, okay, so there are some, okay, so that's an hypothesis, and we believe that this is true for some reason, but it's going to be hard to show. We have some evidence that show that this is reasonable to expect, but on the other hand, we have no proof, so there's no proof, not so much, but we believe that the conjecture is true. And if the conjecture is true, then in fact one can show that pretty high hardness bound. In fact, if you believe the conjecture, one can show that in the L2 metric, you can get 1.73 and 1.27 for k-means and k-median. And in fact, we showed a very surprising result, in my opinion, is that in the L1 metric, the bounds you get for k-means and k-median are the same than in general metric. So in fact, the clustering problem would be as hard in the L1 metric than in the general metric. And but perhaps easier for L2 metrics. Okay, and this is a very nice open problem. We can discuss it more if you want. It's a pretty cool open problem to show that JCH is this Johnson coverage hypothesis is hard. Is indeed the hypothesis is true, meaning that the problem this Johnson coverage problem is hard. And of course, if you can show it instead of 1 minus 1 over e, if you can show it with something a bit weaker, like 0.85 or something like this, then you would still get good. You improve the best known bounds. So that's why it's meaningful thing is that maybe we won't get down to 1 minus 1 over e, but maybe we get still recover some bounds. Okay, and then I'll just finish on a few open problems very quickly.
I have a question.
Maybe. Oh yeah, sorry.
Why do you think it's easier to open the JCH to solve the JCH conjecture than to prove the NP hardness or the NP hardness for I don't know k-means directly?
Directly, because this really try to model what would for all the approach that have been known like since the late 90s, I think this really characterizes how to translate set cover type or covering problem onto Euclidean structure. I mean, if you were to try directly, you need to start from a problem that is hard. You need to start from a problem for which there is a gap already. And if you start from a problem for which there is a gap that is like a covering problem, then the natural way you will go to prove something for Euclidean space is using a framework like this. I believe so. I mean, unless you have like a very convoluted reduction, the natural way to translate the covering problem onto a Euclidean problem, Euclidean clustering problem, would be to go along this path, along the Johnson coverage path. And so that's what.
Yeah, thanks. And there's a question from the audience. Somebody's asking, does this JCH conjecture, is it related to the vertex coverage problem?
Yeah, it is related. If you pick t equals 2, then you recover the vertex coverage. If you pick t equals 2 here, you will get exactly the bounds of vertex coverage. And so it's a way to generalize the vertex coverage bound to something. But what we believe is that for t equals 2, you get the vertex coverage, and it's this 0.9292 that we believe is tight. But now if you go to t equals 3, no, actually it's t equals 3, not 2, but if you get to t equals 5, 7, 8, then the problem gets harder and harder, we believe. But it's a conjecture. So if you could prove it for t equals 4, that you can get fix t equals 4 and prove better than 0.9292, and that would be already like a good step. Like at the end of the day, what we would like is that for any epsilon, there exists a t epsilon such that 1 minus 1 over e plus epsilon is the bound you can't get. But if you can do it with t equals 4 and get better than 0.9292, then that's already good. And using this statement, you will immediately improve the best known bounds for k-means. So like k-median and so on. So it's a general framework that if you get a tiny improvement over this statement, like over the vertex coverage, then this machinery kicks in and you get a harness for k-means. Okay. Yeah, okay, so just to conclude on this, okay, so there is this beautiful problem. So this facility location, which is like a Lagrangian relaxation of the problem, in the sense that, it's the same problem as what we've been discussing so far. You get a set of points, a set of candidate centers, but now instead of a bound on K, which was like, the number of centers you can pick, I give you a cost function from the candidate center to I give you a cost function on the candidate center. And now you can open as many centers as you want. But what you want to minimize is both the sum of distances to the closest center, or distances square or so on, plus the sum of the cost of the centers you have opened. Okay, so it's like a soft version, right? Instead, before I was saying, okay, K is the max, you can't have more than K. Now I'm saying, okay, you can open as many as you want, but you are going to pay, for each of them, you pay the cost, the cost associated. And in here is why I think it's very interesting, is that in the general, this problem is we understand it very well, in the sense that there is a 1.48 approximation algorithm, polytime, that gives you 1.48 approximation, but there is a low bound of 1.46 for the general metric case. So this is almost matching. We have upper and lower bound that are almost there, very close. And now I would like to solve this problem in Euclidean space, L2 distance, okay? Because we believe that the L2 lower bound is going to be 1.2 or something. And on the other hand, if we are already so close from 1.46 in general metric, my question is that can you use the Euclidean structure to beat 1.48 and show that in Euclidean space one can get better than in general metric? From 1.48, I would like to go to 1.45 just to show that Euclidean space is easier than general metrics. If you can prove that for this problem, 1.48 you go to 1.45 approximation, just using a tiny bit of the Euclidean structure, then it would be very interesting, showing that for clustering problem, general metric are strictly harder than Euclidean space. And then we get a bunch of other results that I don't have time to go over now. So, but some recent results that will go into soda about hardness of the continuous version of the problem, where you can't pick your center everywhere. If you have an L infinity metric, then you get higher bounds that was known before. It's pretty interesting. Okay, and I'm gonna stop here and take question and be happy to talk to discuss more.
Thank you, Vincent.
Sure.
Are there any questions? There were some questions during the talk, but if there's something quick, we can.
Yeah, it was pretty long. Yeah.
Yeah. Okay. I guess we can thank you again in the name of everyone with a virtual clap. And yeah, thank you so much. Thank you everyone for participating.
Yeah, thanks a lot for your attention. Yeah.
Bye-bye. Good week, everyone.
Bye.
Thanks.